No, I would not take that bet. I tend to agree with Jeremy on that one.
I think really the question is, can you prove an entire block in less time than it takes to produce a block?
If that's the case, why were we using prime fields to begin with? Why didn't we just use binary fields right out the gate?
That was one of the first questions we asked when we started looking into binary fields.
Well, y'all have given me a lot to think about.
Welcome back to the Rollup, your home for technical talks and open conversations that shape the modular future. Nothing on today's show is to be construed as financial advice. You can see our full disclosures list at therollup.co/ventures. Sit back, relax, and enjoy today's episode after a quick word from some of our awesome partners.
Imagine if the world's GDP moved on chain. Guys, say GM to SafeNet. The newest protocol by Safe isn't a blockchain and it's not a new layer 2. It's a transaction processing network built to send money anywhere and swap anything on thousands of layer 2s from a single universal balance in sub 500 milliseconds. It's fast, it's smooth, and it's simple. And it's built with safe multi-sig level security in mind. SafeNet unlocks smart accounts across multiple chains, allowing users to supercharge security, scalability, and speed. So get started today at net.safe.global and remember to follow @safe on X. GM, welcome to the show. Jim, your first time on. Jeremy, welcome back. Two guys that are very, very in the mix and experienced to speak on the state of ZK. Not going to put you on the spot, but there's just been so much acceleration, so much progress on multiple fronts here. We'll get into a little bit of exactly what you guys are doing in a bit. But generally, I wanted to start off with kind of just wrapping our heads around the latest in ZK. Maybe you guys can give a comment generally about what you're seeing out there, and then we'll talk a little bit about that before getting into the partnership between RiskZero and Irreducible.
Yeah, absolutely. I mean, I think this is a very exciting time for ZK in general. I think we've seen things move from the theoretical to the practical and now to the very usable, even from an economics perspective. We've moved from a world in which ZK was slow, expensive, and complicated to a world where it's really easy to use. And at this point, we've crossed the critical threshold where it's actually less expensive to prove something in ZK than it is to pay for the cost of doing verifiable computing through consensus, right? So we've entered, I think, into a new realm. And what's very exciting to me is that the cost of ZK is continuing to drop precipitously as everyone in the industry is working hard to make things faster, cheaper, and of course, the work that we're doing together with Irreducible will hopefully bring things down even more. But I think it's very exciting to see where we're at.
Yeah, absolutely agree. And I think we're approaching a point where there's a little more stability in terms of the techniques. There's always new research, but we really have very practical systems now. I think about ZK in terms of as analogies to computing, where like when Zcash was around, they were building these custom circuits, which would be the early days of computing. You were making custom circuits, and now with RiskZero and the ability to just run arbitrary code, this is like the CPU era of computing. You just write programs and you run them, and it opens up a whole bunch of use cases. And I think the next generation is when you have hardware acceleration for ZK, and that brings us to the equivalent of GPUs for the gaming revolution.
It's incredible. And I think it really requires like a paradigm shift in the way that people are thinking about blockchains and their mental models here. Because, right now, submit a transaction, it'll get picked up and then broadcasted to the validator set on Ethereum. And then it'll get re-executed a bajillion times. That's a mathematical, technical term. And that is all incurring cost. All of that re-execution is incurring cost. And ultimately we bear as users, we bear those costs. Now, ZK flips this on its head and it says, we don't need to go and re-execute all of this. This is like the original, like Satoshi's vision. That maybe he was the one to say like the don't trust verify, right? Like one proof, and then the verification is so much more concise that we can still hold those same ethical, like practical values without going and spending a ridiculous amount. And I think that's incredible. And I think more and more people will wrap their heads around it. More protocols and applications will come to the realization that these things are not prohibitively expensive as they once were. And ultimately, we're going to see this. It's slowly and then all at once. And we're already starting to see it.
Yeah. And one thing I'd like to just throw in, I think
This,
in the world of consensus, you have a block, and the block has a fixed size, right? There's only so much room within a block for computing. So, as the demand for execution goes up, the costs go up because you have a fixed supply, right? And with ZK, what's really interesting is that you can verify an arbitrarily large amount for the no matter how much you're doing, it takes the same cost to verify. And so, what you can see is that you move from this like scarcity mindset of block space to this sort of abundance where no matter how much compute you want, you can just bring more compute online in an elastic manner, and the cost per compute doesn't go up, right? You don't see this sort of like, gas costs drive rapidly up when the blocks get full, and in the case of decay, it takes, you need to bring some more machines online, but those machines don't cost any more than they did before, and so you have a much more stable cost for computing as you move to sort of ZK verifiable computing versus consensus based. And I think you also, you can reduce things like the fragmentation, right? Because one of the ways that scaling is solved now is you just go do it somewhere else. It's a different consensus domain and another L2 and a roll up, and I think that we'll start to see, you know, the impact of ZK in terms of this, not only reducing cost, but increasing sort of the scale of things people can build, right? Like the complexity of their applications, which I think is going to be very exciting.
absolutely. And Jeremy, you were on recently, but I don't think we got your take on the snarkification of Ethereum. Um, is that something you feel comfortable sharing? Some thoughts and ideas, maybe spicy take if you have one.
I don't. I think I'm pretty much in alignment with where things are going by and large. I mean, I do think that we will continue. I think at where we're at now, it's kind of inevitable already that most things that are being done with consensus will at least be done with ZK as an extra bit of security. And I do think that long term we're going to see uh, the idea of most state transition functions for most every chain will be verified with ZK. That's sort of my general belief.
Yeah, I think
Yeah.
it's inevitable, as Jeremy said. It's blockchains fundamentally are platforms for verifiable computing on shared data, and the way they implemented that before was through re-execution, and so now it's pretty incredible that we were able to take this primitive from the academic literature, from the theoretical cryptography world, and make it concretely useful and able to fulfill its purpose for these systems.
Yeah, it is. I mean, we're turning, the theory is accelerating so quickly, which is really fun. And then we're also applying this in a very practical way, which is scientists and theoretical scientists, mathematicians, like that's the dream, is like to actually solve a problem and not just solve it, but actually see the solution put into practice in the real world and help people is a magical feeling. Um, and so yeah, I mean, I'm also here because of the ZK movement and the acceleration. I think it is only inevitable that we see this integrated into mostly every chain, and so it becomes a question of how exactly will we integrate it. And Jim, I think you guys are doing some really really cool things with Binius. Like, this is something that's maybe a little bit still under the radar and um, not as well known in the space. So maybe you could give us an introduction into Irreducible and Binius and talk about why you're building what you're building.
Happy to. I guess starting with like ZK, it's been recognized that the potential of this technology is exactly what blockchains need, but the thing that was holding it back is fundamentally performance. I think historically there have also been issues with developer experience, but I also trace that back to a performance issue where if it's really cheap and fast to run, then you can sacrifice some performance for usability and still have a good experience at the end. So our mission at Irreducible is to essentially eliminate performance as the barrier for ZK adoption. We believe that hardware software co-design is fundamentally the way you make slow things fast. And so we have a really strong hardware team led by our CEO, Roddy. And, I have a more of a background in blockchain and cryptography. And so we were looking at what are the hardware friendly ways to build ZK snarks. And we identified binary fields as this really overlooked primitive that it was sort of now was the time to bring it back out. And binary fields are a little esoteric to people who aren't deep into math and cryptography. They're basically a mathematical object that's extremely efficient in hardware, that has some really remarkable properties, that's already used widely in deployed cryptography. So it's used in the advanced encryption standard. They're used in QR codes. They're used in AES authentication mechanisms. So they're well known within the cryptography community, and we kind of did the research to identify the way to make them most practical for the current ZK movement. And so we're really excited to be able to take this next step and productionize this with RISC-0.
Yeah, I think if when I first saw the Binius work, it was immediately clear to me that the impact of this as you move toward hardware acceleration was going to be huge, because I think it's very much night and day in terms of the sort of things you can do with binary fields in terms of hardware implementation. And so I think that's a pretty impressive work.
And I want to try to put this into terms that our audience can understand. And one of the most, I guess, one of the most attainable or easy to understand, simplest concepts of the ZK proof life cycle. How you have supply and demand, and you have um, a chain perhaps that is requesting a proof of maybe the state of another chain because it wants to interoperate with it, and so it requests the proof of the state of that chain. um, and a prover comes in, delivers, this is the state of that chain, and I have a ZK proof to prove it, and then that can get verified. um, and so I think one of the pretty reachable in concepts is this proof marketplace idea, where I have a marketplace of provers, um, and I have this demand side of chains that are requesting these proofs, maybe chains or applications, and then I have this network of provers that are all kind of like looking at the bids and looking at the proofs that are out there, and I can submit a proof to earn one of these bids that someone will pay for that proof. Now, is that still the model here with RISC-0 and with Binius? Is it still like, we're kind of like organizing these provers into a network, and then these networks can kind of pick up the bids and supply proofs to their liking? We just have a more optimized way of providing those proofs. These provers can get even better at doing what they're doing, do it for less cost, and ultimately have a more affordable, faster experience for the demand user.
Yeah, I think our goal with Boundless is really to make that whole process very seamless and transparent for everyone on every chain. You should just be able to request a proof, and then it should just get done, and you should have to pay for it. But like to minimize the complexity of that process. But under the hood, there is in fact this sort of market. There's this bidding process, and then the source of most of the cost, when you consider a user who wants a proof to be delivered, the source of most of that cost is related to the proving and how expensive or inexpensive the proving is. And you know, with irreducible's work, the goal is to reduce that cost of that proving. I mean, that would be true regardless of how it was deployed, right? If you ran your own, provers, or if a protocol like builds their own proving networks, however it gets done, that cost reduction still exists. But of course, our biggest interest is, of course, to make sure that these kinds of cost reductions are available on Boundless, so that anyone can, you know, get the savings basically.
And another thing that's really powerful about Boundless and that marketplace model is that you can use the same proving technology across a lot of different protocols, uh, and all these protocols that may have different purposes can all leverage verifiable computing and leverage the same underlying technology, and proving net and proving suppliers to do it.
Yeah. And I mean, if anyone's still listening, they're not convinced on like the purpose or power of ZK, like just take a look at, the things that are out there that are using compute. And NVIDIA is like, one of the most valuable companies out there. You have all of these compute providers that are, that represent big tech. Like all of this compute is being used in various use cases. AI, right, is a major one of them. Um, and the verifiability of this is so critical. Um, and we haven't been verifying a lot of this compute because it has been prohibitively expensive. But with the work that's been going on and with the innovations in mathematics and hardware, we're bringing those costs way down. So Jeremy, could you just kind of sound off and maybe just fill in any gaps here? Because I do want to dig into a little bit more on the binary fields and the Binius acceleration that's at play here. But before we get into that, could you just give us like a high level reinforcement on why verifiable compute is so important?
Yeah, well, I mean, I think if you look at the entire blockchain industry, really the really key features that make blockchain valuable is the sort of fact that you're operating over sort of public, agreed upon data sets, and that the compute is in fact verifiable. And I think that moving that verifiability to something that has a much better scaling properties fundamentally, both in terms of the base cost is lower, but also in terms of this ability to arbitrarily increase the capacity without having to sort of go to a new chain or deal with all these bridging complexities that we currently live with. I think is going to be super huge. But I actually think that, to your point, you're going to see a lot of use cases that are not wouldn't be done traditionally in blockchain because of limitations start to make more sense to verify, right? I think like we're working with Hashflow, for example, who's building a sort of it's effectively a model that's a centralized exchange that's very high performance, very easy to use. But instead of just trusting the exchange, you actually have the exchange be verifiable, and it's done using ZK, and it allows you to have a lot of the same, advantages you would get from centralization, but without having to trust the exchange in the way that you currently do. And I think that a lot of things that are being done now using centralized trusted services will move toward verifiable computing, and we'll really see the we'll see the Web3 blockchain world have increasing capabilities so that the capabilities that it has are much closer to what you see in the Web 2 world. And we'll see, I think, a more emphasis in sort of the Web 2 world on verifiability. And so I think they'll sort of come together over the long course of time. And really, as the cost of verifying compute goes down, there'll be lots of applications where you're like, what? You're not verifying the compute? What are you doing? Right? So.
Yeah, and ultimately that makes a much safer system. Like we're gonna have less FTX like debacles
Yeah.
because those things are verifiable. I mean, heck, I'm based in the US. I think, you guys might be as well. Elon said the other day he's thinking about putting Doge on chain. Like the idea of the entire accounting for the US government in all of its debt, all of its, allocations to different programs and departments to actually have that in a verifiable environment to know that, I'm spending taxes, I'm paying the US government. Where is my money going? Right now, I have zero clue. I don't know if it's going to some military funding program or going to some, garden that's going to get built on a public playground, right? Like I don't know. So to have like some actual insight into where my money is being spent, not just mine, but how all of these things are adding up, you know, we'll it's the open source movement all over again. We'll have more eyeballs and more verification on where the resources are going. And hopefully, optimistically, we can get the wisdom of the crowd into that and we can have a little bit more accountability as far as where things are going. And it's not just the resources of a nation state or a government, but it's all of things that are considered valuable, whether you want to consider resources and money valuable at the state level, or you want to take like an AI project, AI model, and the weights and the tokens, and make those verifiable as well because they're valuable. all of that can be done in a verifiable way if the costs of proving come down such that it is still profitable to verify the compute. And so again, Jim, what you guys are doing at Irreducible is taking on a new type of ZK process. You're going from, and this is where I'm going to start talking like a little bit over my head, but I'm going to do my best, and please correct me. Like, previously we were doing finite fields, if I'm correct, and we were computing over finite fields to generate these proofs, and that gave way to some of these proving systems like Starks and Snarks. Okay, now we're going from finite fields to binary fields. Please tell us what that means and why it's important.
Sure. So to be clear, binary fields are a type of finite field, but they're pretty special. So previously, all of the systems used another type of finite field, which are prime fields, and they're maybe a little easier to understand. But binary fields are really powerful for a few reasons. As I said before, they are already kind of a standard in cryptography because they have noteworthy properties. They map really well to binary systems, which are, computers are binary systems. So Jeremy and the RISC-0 team have built these systems that emulate a regular CPU architecture, which is RISC-V. RISC-V is it's a computer system that's meant for instantiating with a binary circuit that has zeros and ones in it, and all of the registers and the memory addresses have 32-bit banks. And so when you work with prime fields, there's a pretty fundamental mismatch where you have this kind of weird mathematical object that doesn't quite fit into bits, but you need to use that to emulate a digital circuit that's fundamentally created for the world of bits and Boolean circuits. And we think that binary fields map way better to this for a few reasons. You have these binary fields can be a perfect number of bits, right? We have some that are like 8 bits, which is like a byte. So you can take a byte of information and perfectly encode it into a binary field, or a 32-bit integer, which is your kind of fundamental register type in RISC-V, all the way down to a single bit. The Bineous system can efficiently operate with single bits. And that was one of the properties of our research work that really made this the benefits of this approach shine. So we think that basically the overhead of translating a system like RISC-V into the binary field world is a whole lot lower than what it took to do it with prime fields, and that's why we're excited about the potential speed ups that we'll get from doing this.
Yeah, I mean, I think another way to state it is that prime fields, while they're mathematically a very pretty thing, they don't really. It's hard to translate things built for the digital binary world into sort of the traditional prime field arithmetic that's used in these proof systems. And similarly, that prime field arithmetic is also not super easy to build into digital logic under the hood, right? So you've got something that looks like a digital circuit, which is the RISC-V circuit over here, and then you're putting it into this strange, prime field world, and then you're converting back from that into the actual digital logic that runs it, running on a GPU or a CPU. And so if you can make things in binary, it's both, you get less overhead. It's much more natural for both, taking something that's meant to be a binary system like a RISC-V, and then also for how do you implement that resulting thing in hardware. So I think it just gets rid of a bunch of the impedance mismatch, a bunch of the places where the parts take a little bit of extra work to put together. And so there's a big efficiency gain you can get by doing it that way, which we're very excited about.
If that's the case, why were we using prime fields to begin with? Why didn't we just use binary fields right out the gate?
It's a really good question. That was one of the first questions we asked when we started looking into binary fields, because there were some early papers that were very, relevant and influential to the systems that everyone's been building that did use binary fields back in 2018 and 2019. And we, on my team, myself and our researchers looked at this, and it sort of seemed like the trail went cold. Like there was this mystery when people were talking about binary fields, and then everyone stopped talking about binary fields and switched to prime fields. And this is for a few reasons. One, the benefits of binary fields are extremely apparent when you're building custom hardware, but when you're running things on a computer system that has, accelerated instructions for integer arithmetic, the benefits aren't as immediately apparent to like a regular software developer. So that's one reason. Another is there are some mathematical challenges that you need to overcome in order to use binary fields. Frankly, they're weirder. Like if you haven't studied math, they're not as familiar of a concept as the integers modulo a prime number. So those are some of the things we had to work through. But when you get past that, you see the substantial benefits. I mean, one data point that we investigated on our team is we looked at the efficiency in creating an ASIC for binary fields versus equivalently sized prime fields, and found that when you take into account the clock frequency that you could run a chip at and the number of gates required, it's around a 7 times efficiency gain to use a 32-bit binary field as compared to a 32-bit prime field. So those are the things that were kind of fundamentally motivating us to say, okay, let's figure out how to make this work.
Does that translate into a 7x performance improvement? Is that a one-to-one comparison?
It would. I think potentially it's more than that, because there's like outsized advantages to fitting more logic onto a single chip. If you need to do more proving work and you don't need to communicate between two different devices, you can have like an outsized performance gain. So, but yeah, like at a first approximation, that does essentially translate directly to proving performance and efficiency.
Love it. And Jeremy, from the RISC-0 or RISC, ZKVM side of things, like what is the integration process here? Is it just a matter of, is there an upgrade process? Is it integrating to hardware? Like generally, how does, once you see this kind of performance in a theoretical, like simulated environment, how do you go and you implement that practically?
Yeah, so I mean, I think with what we're doing right now is, so we have built the sort of circuit, the set of constraints that emulate the RISC-V, and we've built that on top of existing proof systems. And we need to sort of go through those set of constraints and adjust them to make them work in sort of the binary field version of the world. And so largely it's really sort of taking and doing a revision of our RISC-V circuit to make it work in that new world. I think what's interesting is actually we're actually taking this opportunity as well to sort of take some other really great ideas that come from the Irreducible team. They have this new arithmetization, M3, and it's sort of a different way of looking at the problem of how do you build a circuit in a stark way that sort of decomposes the problem in what we believe is like a nicer, more. It makes it easier to build circuits. The circuit's more flexible, more powerful, and so we're actually, I think, going to support both our existing proof system and Irreducible using this sort of new way of looking at how to build a circuit. So I think the next rev of our RISC-V circuit is going to sort of use this new approach, which actually even on the prime field side gives us a number of performance benefits because it allows it. You can reuse certain computations more easily. So rather than decoding, now I'm getting a little overly technical here, but rather than taking and decoding an instruction every time you run the instruction, you can actually decode it once and then reuse that decoding over and over again, sort of mostly for free based on this sort of new sort of arithmetization model that comes from the Irreducible team. So we're excited about it across a couple of different boundaries. But effectively, the short version, to answer your original question, is we just really need to sort of re-engineer the RISC-V circuit somewhat. Luckily, we have a lot of experience. We're actually already on our sort of third generation of that circuit. We've learned how to build RISC-V circuits really efficiently at this point. So we're definitely excited about this next one.
Redstone is DeFi's modular oracle, supporting over 100 clients on over 50 chains and offering 1,000 assets. Redstone is the leader for Bitcoin staking and yield-bearing assets. They offer the most robust, customizable price feeds available in any model. Join the Redstone exhibition today. Yep. I saw something the other day. It was like I think it was an experiment that someone had done. It was Yuki from Sorella Labs that posted this, and I think it came from from a report. It looks like by Pi Squared, where they went and they analyzed all these different provers across some different proof types. It looks like, um, or excuse me, some different experiments in terms of logic. So they went from like basic logic, very small, to a very large data set of logic, and then also they used ERC20s from small to large, and it looks like Risk Zero came out on top on for Yuki says 6 out of 8 of those tasks. Um, and then there's also a chart below that kind of lays out like a comparison when I think it's the size of the data set. When the size is relatively small, Risk Zero does quite well. And then there's maybe some different optimizations that could be done, or things that are done a little bit differently as the data set gets larger. I guess I'm curious, like, you know, when you guys are thinking about like the way to optimize, and maybe there's trade-offs, and ultimately there's trade-offs. How do you guys balance that? What is the reconciliation process, or when you guys are looking at a set of trade-offs, how do you guys make a decision on which way to optimize?
So I would say that the short version is that it's a little bit of intuition, but generally, if I have to pick one thing or another, I tend to ask myself which one would make proving Ethereum run faster. And that tends to be sort of my general North Star, in the sense that it's a good representation of sort of what kinds of problems are being done in the where the near term use cases for ZK are. That said, I think one thing to note is it's very rarely about trade offs. It actually tends to be more about we've seen this, like, I think almost every quarter there's a at least a 3 or 4x speed up of ZK systems across the board, and that's not just with our system. That's industry wide, right? We're seeing everyone's making their stuff faster all the time, and I think that one of the really things that's interesting is, um, you know, where things are now, it's almost hard to keep up with the benchmarks, right? Like it's like, oh wait, they just upgraded to the next version. Oh wow, this system now runs 2 times faster, or that system runs 30% faster, right? Like, and so I think that you're going to see a lot of sort of back and forth in terms of performance numbers, as everyone's driving down toward where the bottom is. And I think from our perspective, we're really focusing on, 2 different fronts, right? One front is what do we do to take the existing system that we have and to like speed it up here, speed it up there, and there's like 20% bump on this and a 50% bump from that. But also sort of the bigger question of, okay, over the course of like a year or 2 years, where are things going, right? And I think that, so in that regard, like I think, the project with Irreducible is more of a significant bit of engineering, that's going to take a little bit longer to get done, but also will be yet an even bigger step function in terms of performance, right? I think eventually we'll probably hit the bottom, but we've still got a long ways as an industry, because there's not only the improvements to the RISC-V system, there's the improvements to the proof systems themselves, there's improvements to the hardware acceleration and building them closer to hardware, more modern process, right? I mean, at some point, it's got to not be a 2x every couple of weeks, but as it sits, there's a lot of things to improve. There's things that are on our list that are like, oh well, that's a 10% performance improvement. We'll get to that when we're out of all the easier ones, right?
Right.
There's a lot.
Yeah. Or the ones that are 50% improvements, those are going to take priority.
Yeah.
We're looking at Moore's law in the rearview mirror.
Yeah.
That's incredible. And yeah, I mean, you say this is a race to the bottom in the best way possible, right?
Yes.
Like,
And
Yeah.
industry wins from it, right? Like,
Right.
so. Mhm.
Yeah. So, I mean, is there even, it seems like the bottom is, and we're talking about bottom in terms of cost, right, to proof, which is great for consumers. So, is there a bottom in sight? If not, is there a theoretical bottom, like, you know, mathematically?
I mean, clearly one can't make ZK proofs faster than you can run execution, right? It can't be ZK is slower than running it without ZK, and clearly there's going to always be some multiple of performance versus not verifying it. But how close that can get to one, I don't know that we could probably make some back of the envelopes based on our current theoretical understanding. And I think to Jim's point, the theoretical breakthroughs have been slowing down. The amount of engineering to catch up with the current latest theory, though, is still quite vast. Um, and yeah, it's unclear if the theory is done or if there'll be more on the horizon. I don't know. Jim is probably more able to talk to that than I am. He's a little
Yeah, I'm not like I think that the research is coming a long way. I still think that having true dedicated custom compute and custom hardware for this stuff is going to be, a step function. It will be a new world essentially when we're actually running verifiable compute on chips that are designed to do it. And, why do I think this? Among other things, we can look at analogies to other industries like the Bitcoin mining industry, where if you were asking yourself where's the bottom when we were still in the GPU mining era of Bitcoin mining, you kind of wouldn't have been asking the right question at the right time. And then when you're looking at graphics, they made custom computers for doing graphics processing. Those are video cards and and GPUs. So that's, I think after we get to the point where we're actually running the entire proving protocol or the entire proving process on a device that is custom designed for verifiable compute, then we can start asking the question like, where's the bottom of cost efficiency?
Yeah. And we're going to get there. Like, these things, the hardware is going to come out. In theory, like you said, we are getting as close to real time proving as it gets. Like, is that and when we're thinking about like how fast can these things go, like obviously the cost is almost a little bit easier to measure. It would be, the cost of execution essentially, and then just in a one node system, right? Because there's no re-execution. So when we're thinking about real time proving, like Jeremy, I think this is something that you guys like have really ran with. What is the philosophy around real time proving?
Yeah, I mean, I think what's interesting is that we will probably get to real-time proving before we get to the maximally performant ZK systems, in part because, not only are we improving in terms of the cost and the speed of all of these individual proofs, but we're also improving in terms of the ability to split this problem up across parallel machines, right? And so the first thing that will happen is that you'll be using a fairly, you know, decently large amount of hardware, but you'll get the proof done extremely fast by properly parallelizing the work, which we already do, today, and support in Boundless and in the work that we're doing. But I think that, and then what will happen is you're just going to keep that same, latency and speed and just start needing less and less hardware, and it'll become more and more inexpensive, right? So I think there's a couple of different axes on which this, happens. But yeah, I think we're. I think that real time proving is at least at the sort of level of requirements for Ethereum this year problem. To be honest, like
And could you remind us like what are kind of like the benchmarks when it comes to real time proving? Is it a certain amount of like latency and cost, or what? Or
yeah, I mean,
excuse
it's
me,
really
just
like
really just latency, right?
I think really the question is, can you prove an entire block in less time than it takes to produce a block, right? And with some of the work, in terms of the current sort of roadmap for, there's really two different sort of levels. There's the question of, can you produce a block in time for the next block, which works for some models, and there's, can you actually produce it within the same block, right, which is a little bit harder. But I think that I think many blocks are in the sort of 30 to 40-second range, already, and so I think we're getting quite close. I think only a few more. We don't even need. There's not even need requirement for a factor of 10. It's like a factor of 2 or 4 or whatever. Like, the numbers are going down so fast it's hard to almost track it. But it's. I, if I would be very happy to bet someone that before January of next year, that real-time proving will be a practical reality.
Jim, would you take that bet?
Sounds like a pretty good. No, I would not take that bet. I tend to agree with Jeremy on that one.
Okay.
And that's why we think that, I mean, latency is really important for a lot of use cases and for protocol design and for user experience, but it does seem solvable with enough parallelization, as Jeremy said, and which is why we fundamentally care about cost. And when you reduce cost, it opens up new use cases. Like you can push transaction volume, but you might also be able to get to a lot more use cases with client-side proving and actual privacy-preserving zero-knowledge proofs, which an end user is not going to have a rack of GPU-equipped servers or something available to them. But if you can get the entire proof running, real time with less hardware, then that's really powerful.
Yeah, I want to chat about that just for a little bit, kind of in these few minutes here, because I was on a live stream just the other day with a founder of a ZK proof marketplace, and I was kind of laying out this vision that I've heard from some of the local consensus maximalists, like the guys at Anoma. If you've talked to them, like, they're excuse me, and One Balance too. Stefan over there is really good, and Adrian at Anoma. They kind of talk about this idea, and we are the rollup, like modular rollups, thousand rollups, million rollups for everyone. And taken to the logical extreme, it's like every user has its own state that it operates on and it conducts transactions on, and we are each user has that state, represents that roll up, and runs, I don't know exactly what the right terminology here is, but runs the logic to coordinate transactions for that state. So, I was kind of laying out that vision, and this founder said, that's great. Maybe we'll get there, one day, but it still makes sense to delegate the proving. We shouldn't rely on client side proving. But for that reality, the client side proving is what kind of brings about the local consensus, and everyone being able to verify and prove their own the state of their own state, if you will. So when it comes to client side proving, what are the blockers? Like, even if it could be something that even if it's something that we could do, is it something that we should do? Is maybe the first question, and then what if so, how do we do it?
Yeah, I mean, we're actually working on our sort of plans and our roadmap for client-side proving. We have actually done some experimentation on client-side proving. Our prover actually currently runs on the iPhone. It's not really production ready yet, but we actually our stuff supports metal acceleration, and the iPhone has metal GPU acceleration, right? I think though what's interesting is the way that we will likely see this come about. It is harder and more expensive, or sorry, not more expensive, but it's just a harder technical problem to make client-side proving sufficiently fast. And so what I think we'll see is sort of the long-term state may look a lot like a lot of the work does get done client-side, and clients are meaningfully able to participate and be participants in this network of provers overall. I think what we're going to see as a starting point, though, is this idea that some particularly privacy-critical components of the transactions will move client-side, whereas the general less privacy critical things will still be done through sort of a marketplace of provers where people have like high efficiency dedicated hardware for those provers. I mean, at some point, maybe Apple phones will come with an irreducible hardware accelerator built into them, at which point it will be a no-brainer. But I think in the meantime, there are places where you can do most of the protocol, you know, in an open public network, and only portions of it that are actually privacy sensitive, like doing a Merkle check of or a private coin transfer or whatever can be done client side, and that amount of work is much smaller and more constrained, and is much more reasonable to run the client side prover.
Yeah. And there's some interesting technical points around this. So one thing that's unique about client-side proving, they might have metal, GPUs in Apple devices, and you might have a GPU, but we typically think of clients as being more memory constrained. So you need to create proof systems that consume less memory in order to produce a proof. There's also ways to shift the trade-offs of how to prove something, where you might find ways to create a zero knowledge privacy preserving proof that has a really large proof size, and then delegate the compression of it trustlessly to a prover network at that point. And I think that as we can explore models like that would become really interesting and give users privacy guarantees, but also get the efficiencies of like having economies of scale in terms of data center deployments and custom hardware for doing the really heavy lifting.
And I would say, even if client-side proving does become easier, there will always be a place for these larger provers available over the network, because there is just fundamental economies of scale that are, we see there's a lot of value in cloud computing today. And I think at the end of the day, it will always be less expensive per unit electricity or dollar cost to do something on a bigger iron than it is to do in your phone. But I think that you'll end up with a model where there are both. But I think this idea of decentralizing even further is a really very plausible direction for the sort of, almost like everyone has their own roll-up, is actually, I actually think, if you look at it, there's a lot of places where you don't actually need full consensus. You just need a non-repudiation and verifiable computing, that you can actually build sort of a much stronger connection between things that would otherwise be in different consensus domains. So I actually think we'll see this type of changes, but exactly how it's going to play out is unclear at the moment still. So.
Well, y'all have given me a lot to think about, and I really do appreciate the conversation. I always, walk away from these ZK conversations. It's with people smarter than myself. I learned so much, and I really appreciate you guys taking the time to have this conversation and talk about the work that you guys are doing, and also about the state of ZK in general. I hope everyone listening also learned as much as I did.
Well, it was wonderful talking to you. Always really interesting discussions, for sure. So
yeah, thanks so much. This was really interesting.
Thank you.